Hello, we're going to start astronomy with talking about how the Earth moves and motion. So basically, what's Earth's motion? But first, we have to figure out how we know something is in motion. And if you look at this GIF of a swan, you can see that the swan is pretty actively attacking a sign that ironically says "Caution, Swan Aggressive." Now, the question you should be asking yourself is, how do you know the swan's moving? What are you comparing it to? Well, in this case, we're comparing the distance from the swan's beak to that sign and the distance from the sign to the swan's body. You can also tell that the swan's head is moving in reference to the two trees behind it. So, in movement, we need to have a comparison point. We need to have a reference point to show us that an object is in motion. So here's a swan. It's a little harder to tell, is that swan in motion or not? By the way, that swan is carrying its babies on its back and keeping them safe as they're going for a little swim. And we think it's probably moving because we do see some ripples coming out, but that could be bobbing up and down. But because we don't have a reference point, it's much harder to tell if it's just kind of, going in circles or if it's moving one way or the other. Where this one, where I can literally see the swan's head moving in reference to these two trees, I can tell because I have a reference point that that swan is moving. This one's a little harder to see. So how do we know something's in motion? We have to compare it to a reference point to see if its distance is changing from one point to another. So what is motion? Can you tell me what's in motion here? Well, if you said the apple, part of it is because it's spewing out the back and the front, but the thing that was in motion actually was the bullet. It actually entered through this side. There's the entrance hole. Here's the exit hole. It made pie. So the definition of motion is an object is in motion when its distance from another object is changing. That's the definition of motion. So even right now, while we're standing still, you are moving incredibly fast. Now, if we were in the classroom, I'd be standing up and spinning in circles and rotating around something that looked like a sun, and then we'd be showing all that, but that's a little harder to show on video, so we're going to just discuss it. So right now, standing still, in just one direction of motion, you're traveling 30 kilometers a second. The Earth spins at about 5 kilometers every second, so we're moving half a kilometer every second. Every 2 seconds, you've moved a full kilometer. The Earth revolves around the sun at 30 kilometers per second. So just our path as we orbit the sun is occurring at a rate of 30 kilometers a second. Not 3 kilometers, not 0.3 kilometers, 30 kilometers per second. And so we spin on our axis, we rotate on our axis, we orbit around the sun. So we're spinning and going around the sun. And then that whole solar system is spinning around the galaxy. And because it's spinning around the galaxy, we're traveling at 250 kilometers per second in another circular motion. The Milky Way, the whole galaxy, is being flung out from basically the Big Bang at 300 kilometers per second. So we're moving at one time while we're sitting here in 4 different directions. Now, why don't we get sick? I mean, that's a lot of motion. Well, it's kind of like, think about if you're in a car. Have you ever been in a car and taken a ball or had something in your hand and you tossed it up and caught it and it came back to your hand? Well, the interesting thing is, because relative to the car, you aren't in motion, but the car, relative to everything else, is in motion. It's also the same reason why technically you're not really doing a lot of distance when you're in a plane or speed, but the plane is, because relative to the seats within the aisle, you really aren't moving. And you have forward motion with the plane, you have forward motion with the car. So if I was in a car and I was throwing this rock up and down, from my point of view, this would be going up and down. But from somebody outside, they'd see me throw it up and it would land down. It would actually form a parabola. And that's because the rock and myself have the same forward motion that the car has. In other words, never adjust your seat, if you have one that you can hand release, at the same time you throw on your brakes, because your forward momentum will make your seat fly forward. That's why we actually have locks on seats, so they can't do that. So we don't get motion sick because of all that motion because we're acclimated. From us, we'd have to look at a reference point to determine what's in motion. Well, we do know motion is occurring because we see the sun rise and set every day. We see the moon rise and set. We see the stars rise and set. But the sun is 93 million miles away from us. It's really quite far. So we perceive our motion as we rotate on our axis as the sun rising and setting, although it's really us that's doing the moving. The sun is in the center of our galaxy. We're just spinning on our axis. And because we're spinning on our axis, we see the sun rise and the sun set. We say it's the sun rising. It's really the earth rotating. Well, because our reference points are so far away, we don't really get motion sickness. If you ever watch a dancer or a skater spin, quite often they spin around and they have their eyes focused on one part and they spin and then they whip their head back to see that same point, so that it's how they control the motion sickness. So we have to be careful with that. Now, if something happened and all of a sudden something massive like a planet collided with our planet and we stopped the motion, the interesting thing is the planet might stop rotating, but because we had that same forward momentum, just like you would in a car, if you slammed on the brakes and release your seat, you're going to fly forward. Or you guys know this, if somebody slams on the brake, you do fly forward. That's why we have seat belts that stop us from that forward motion. But let's say, this is not, you don't have to worry about this, but let's say a planet hit our planet and it stopped its motion, it stopped its rotation, it stopped spinning around the earth and rotating around, well, we'd still actually be rotating around the galaxy, but let's say it just stopped two of the motions. It stopped rotating on its axis and revolving around. We would literally fly off because we would have forward motion. Anything not physically attached to rock would fly off. Now, gravity would probably pull us back down. That would not be a good thing. But we don't experience that because we just continue to rotate on our axis. We continue to revolve around the sun. And we don't perceive that because our reference points are so far away. So we don't get motion sick because we're moving this fast. But really, if you think about it, you're spinning at 0.5 kilometers per second as we spin on a course around the sun at 30 kilometers per second, as the whole solar system is spinning around the spiral arm of our Milky Way galaxy at 250 kilometers per second, and the whole Milky Way is flying out in a straight path at 300 kilometers per second. We're going to show a rendition of that in just a bit. Now, here is where you're going to just pause in the video, and then you're going to go and do these questions. If the Earth travels at about 30 kilometers a second in its orbit of the sun, so we're talking about its orbit, how many kilometers does it travel in 1 minute, in 1 hour, and 1 day? Now remember that we're talking about 30 kilometers per second, so it travels 30 kilometers for every second. There are 60 seconds in 1 minute, so to find 1 minute, you have to take that 30 times 60 to get your answer. Now, once I know that answer, I want to know how many kilometers per hour we're going. So now, once I know my kilometers per minute, remember there are 60 minutes an hour. So I just take that answer and multiply it by 60. If I know how fast I'm going per hour and I want to find out days, remember there are 24 hours in a day. So then I take that number here times 24 to get that. And once I know how far I travel in 1 day, I can calculate the year by taking that answer and multiplying it by the 365 days in a year. Except really it's not 365 days for 1 year. It's 365 and a quarter. And then actually there's some adjustments that happen on years that end in double zeros. So we'll talk about that in shortly, but you just need to know that it's roughly 365 days for our purposes. Leap year fixes that last little bit. So stop, do the math, then come back and resume the notes. Okay, you should be back. So we talked about the fact that we actually are rotating around in our galaxy at, what was it? Do you remember? There it is, 250 kilometers per second. We're moving around the Milky Way. And it's called the Milky Way because there's one part of the sky, if you look at it, it's very milky, and you're actually looking into the center of our Milky Way galaxy. That's why we call it the Milky Way, because it kind of is blurred out. There's so much light. In fact, if you were in the middle, there's so many stars there. We're kind of in this perfect Goldilocks thing, because we can actually see other solar systems. We can see other galaxies. We can see other stars, because we don't have our nighttime sky completely obliterated with light from other too closest stars. If you were in this galactic center, you would actually not really be able to perceive this whole outer space thing. Not without the aid of, like, you'd have to have some kind of radio telescope, but there's so many stars that might interfere. So you'd really be looking at X-rays or other things that would allow us to figure that out. Here's our solar system. We're in one of the spiral arms of the Milky Way, and we're kind of in the way out rural. I mean, you got the city, you've got the suburbs, and then we're kind of out in the very rural area. In other words, there's not as much around us clouding our night sky, which is a cool thing. So we're here, and if you look at this, there's quite a distance across this solar system, and we'll talk about that in a little while. But for right now, just know that we are located in a spiral arm. We are not towards the center, but this is our location. This is where we are, and we're spinning around this galaxy. So, how do we know if stuff is moving towards us or away from us? Well, we do something called Doppler shift. And Doppler, you've heard this, it's that, you know, that high-pitched sound as something comes towards you, and then as it passes you, you get the low-pitched sound. Well, the same thing happens with light, except in the color spectrum, blue wavelength is much shorter or compressed compared to the elongated red wavelength. So as something comes towards us, it pushes the waves closer and closer together, creating a slight shift in the color spectrum to blue. Where if it's pulling away, as this gets pushed closer together, this pulls apart, spreading out those wavelengths. And so as it moves away from us, we get a shift towards the red. So here, red shift is moving away, blue shift is being compressed and coming at us. And by the way, these are some Hubble Deep Field Telescope pictures. And what you're seeing here, these aren't all different stars. These are all different galaxies. There may be a few wandering stars in there too, but these are galaxies. A lot of what we think of as our constellations, some of them are stars, but some of them are actually really far distant galaxies that make up part of our belts. And we'll talk about that in another set of notes. But if you look at this, you'll notice that this galaxy is slightly shifted to the red, where this one is shifted to the blue. And that's telling us that this galaxy is moving away from us, where the blue galaxy is coming towards us. Doppler shift, that red-blue shift, where red is away and blue is towards, we'll be talking about quite extensively between this unit and meteorology. But in meteorology, we'll not only use light as an indicator, but we can actually use sound. And so Doppler effect is a big thing in science, where you need to understand that it can apply to sound and it can apply to light. We use Doppler radar to find things out. So again, here's a red shifted galaxy, here's a blue shifted. So the study of the moon, stars, and other objects is called astronomy. Ancient astronomers studied the movement of the sun and earth. They thought the earth was standing still and the sun and the moon were moving. We later figured out that actually we're not the center of everything. The sun is the center of our solar system, but as you saw, we're not even close to the center of our galaxy. But it's actually, the earth is rotating on its axis, causing us to appear like we're the center. But really, the sun is the center, where we are revolving around the sun. And we are rotating on our axis, and the moon is also moving around us. So they were right, the moon is moving around the earth, but the earth is moving around the sun. I need you to pause here, and I am not going to try and play this video in a video because it's too hard to hear. So I need you to pause the video of me, and would you please watch this 3 minutes and 50 seconds, and it's looking at the alignment of the pyramids and their use of ancient technology to figure out where we were. In fact, they were much better at knowing what was happening in the heavens and using that knowledge. That's why we have the constellations, because people were observers of the sky, and they would make up stories, and they would see these different constellations come through at different times of the year. And watch the video, then come back. Thank you for watching the video. Here we go. The sun and moon seem to move mainly because the Earth is rotating on its axis, and that imaginary line that passes through the Earth's center from the north to the south poles are called the Earth's axis. The spinning of the Earth on its axis, remember, is called its rotation, and Earth's rotation on its axis causes day and night. It takes about 24 hours to rotate once on its axis. The interesting thing is, what most people don't realize is our 24-hour day actually shifts. If we have a really bad hurricane or a massive earthquake, those things can actually speed us up or slow us down on our spin. We average 24 hours. It's close enough that we don't really kind of take it into account, because you're talking microseconds of change. But it does change. In fact, if you go way back in Earth's history, when we were just coalescing, we were spinning around something like once every 6 hours. We were really whipping around, and the moon used to be like really close to us. So yeah, over the last 4.5 billion years roughly, we have had some changes. The moon is getting farther away from us at about an inch a year, and our day has slowed from a 6-hour day to about a 24-hour day. So rotation occurs on its axis, causing day and night. We also have our revolution around the sun that causes our seasons. And here's an interesting and testable question. We are physically closest to the sun, guess what? In the northern hemisphere, we live in the northern hemisphere, during our winter. We are at our closest approach to the sun because we have a slightly elliptical orbit. And our closest path to the sun, where we go here, is summer in the South Pole, but winter at the North Pole, which means it's our winter. And in the summer, during the equinox, we are actually physically in the northern hemisphere, the farthest we are from the sun. So the sun distance can affect us in this like 23,000 year wobble that we'll talk about in a minute. But that's a whole different thing. And actually that wobble will eventually change it so that it will be summer in January and winter in June. But again, you've got about 14,000 years before you have to worry about that. So I kind of don't think in our lifetime we'll have to really worry about the wobble affecting our seasons. But it does over long periods of time. Now, again, winter, northern hemisphere. And you can see this if you look at this. The northern hemisphere, in our winter, we are the closest to the sun. Summer, northern hemisphere, see this northern part of this pole is facing the sun, so we're going towards summer. This isn't shaded right. We should be in shadow up here, so just kind of ignore the shading. But again, we are the farthest from the sun in our summer. So the real cause of the seasons is our rotation, is our day, but our tilted axis means that in the summer, the northern part of the North Pole is pointed more directly at the sun, and in the summer, the South Pole is pointed more directly at the sun because it rotates at this 23.5-degree angle around the sun. So here, the bottom, South Pole, would be facing the sun, but over here, the North Pole would be facing the sun. And that's what causes our seasons. It's that 23.5-degree tilt from the elliptical plane. It's kind of like, we think one of the reasons why the moon is here is because a big planet early in Earth's coalition slammed into it, spinning part of it off to create the moon. And we think that impacts like that actually kind of knocked us sideways. In fact, when we look at the other planets, you'll see some are like knocked 90 degrees. So if you look at the distance that the sun and the Earth during different seasons, we actually are the closest, remember, physically to the sun during the northern hemisphere. I am going to turn this sound off because you don't need to hear that. And We all know Schoology loves to play videos sometimes, but I do want to show you this progression, and I'm hoping it will load. Here we go. So this is the wobble effect. This is that 23,000 year roughly wobble. It's called precession, where the axis is tilted and it wobbles and tilts in a different way. So you see it going towards this 23.5 degrees. And it will show us the zodiac. And basically the zodiac are those main constellations that different ones appear in different seasons. So in summer, you can see the northern hemisphere is the farthest from the sun, but it's pointed towards the sun, so it's warmer. It's getting more direct rays. While the southern hemisphere down here is not. Now, as we move towards our equinox, which is occurring shortly, the day both the North and the South Pole were lit. Now in winter, the North Pole is in dark and the South Pole is in summer. They're in light, and we are the closest to the sun in our northern hemisphere. So the axis of rotation again is 23.5 degrees. But we also have this wobble, like a top wobbles. And do you notice that the sun is where we reference it, but this wobble or precession actually points at different things. And because that wobble occurs, it takes about 23,000 years. I'm not going to make you memorize 23,000 years. I need you to however, know that the wobble affects the position of the Earth. So in another about 14,000 years, it's going to change. That wobble is going to change the tilt going in a different direction, so that in the winter it will actually be, well, hot in January and cold in July. Now you can get that if you go to the southern hemisphere. We're basically going to flip our hemispheres. And as it keeps going, it actually will change over time. And there is that precession. That's the wobble, and it takes a very long time to complete it. Again, we're not going to need to worry about this in our lifetime, but you need to understand that we rotate on our axis, we revolve around the sun, we revolve around the galaxy, but on that rotation of our axis, there is a wobble that occurs, and it changes winter to summer and summer to winter in the months where we assume it is. So you could have a frosty Friday in July instead of a frosty Friday in January. All right. The other thing it's going to show you is that right now, our rotation, our axis, is pointed towards Polaris. When it goes as far as it can the other way, Vega will actually be our North Star. And I wanted to show you this. This is actually a picture from my lake lot. And this is not, it's not the winter solstice, because to be honest, it's hard to get in here with snow. But this was November of about a year and a half ago, 2 years ago. And you can see how far to the south the sun is. This was close to the summer solstice about 2 years ago, and it's traveled much farther north. This set of trees right here is this set of trees right here. This I took 2 nights ago, and you see that it's actually between those trees. So it's about halfway. We're, by the way, remember, roughly the 21st, 22nd of September is our autumnal or fall equinox, where we have 12 hours of day and 12 hours of night, and then we have more night than we have day. It's the spring equinox, the vernal equinox, where we start gaining daylight with more than 12 hours. And the reason I throw this little bit in here is because, well, this was taken 2 days. It was taken tonight, for me, if you're watching it, but this was taken 2 days before the fall equinox. And this is the year that I'm recording this, that we had really big, huge, massive fires in California, and that smoke has made it to Minnesota. And because of that, this was the sunset tonight. It literally looks like a little alien. It looks like somebody took a picture and plopped a circle and colored it in. But that is the sun tonight, and you're seeing that because when the sun's light goes through all that smoke particulate, it scatters the red light, and you get these beautiful red sunsets. It was just amazing to watch, but it looked on the video or on the photo just completely fake. But that is due to the haze of the smoke from the California fires. So again, Earth's wobble, sorry, it's 26,000 years. changes its position over the course of 26,000 years. It's called precession. Right now, our North Star is pointed towards Polaris, and eventually it will be pointed towards Vega. So, if we look at this, again, you can see day and night. So this is the rotation on our axis, and you can see the wobble starting to occur, and over long periods of time, you can actually see the wobble happening. And it gets more and more pronounced the farther out we go. And don't get sick, turn it off if you need to, or you can come back and replay it. But this is looking at what happens as the wobble occurs farther and farther through time. If you have a chance, go ahead and watch this video. It's quite interesting, but I'm not going to take the whole time to do it. Maybe just a little bit, because this is again looking at that 23.5 degree angle to the ecliptical plane. In other words, our equator, the center that rotates, is shifted 23.5 degrees. So I guess maybe I'm going to go through this, but I am going to turn the sound off. So here is that wobble. It's that ecliptical plane rotating as it wobbles around every 26,000 years. So go ahead and watch that if that helps you. Here are a couple of questions. Now look at this very carefully, because test questions will look like this. The North Pole is in shadow. The South Pole is lit up. That means during our winter, the North Pole is in shadow, which is winter. The South Pole, then when we have our winter, is in sunlight, so it's their summer. So according to this, we would need to be in winter. So it says at point B right here, what would you see? Remember, the Earth rotates on its axis counterclockwise, so that means it's going this direction, from here to there to there to there, which will actually be needed on the next worksheet. So at this point, if it's rotating from A to B and then B to C, B is going from the light into the dark, which means that's not sunrise. That would be on the other side of the Earth. It's not noon. That would be A. It would need to be sunset because it's setting. We're going from daylight into dark time. If you go a quarter of the way around to C, that's going to be midnight. If you go a quarter of the way around here, if I had a D over there, that would be your sunrise. Quarter of a turn to A, you're full dead on to the sun. That's your noon, and then back to about 6 p.m. or dusk. So, which people would see the sun? Well, A could see the sun, B could see the sun. The only sunlight C is going to see is reflected off the moon. So it would be A and B. So I actually answered 2 of your questions for you. As always, if you need help, I am here. Email me, jump on Zoom, or ask me in class, whichever one is appropriate. Thank you for watching the notes. If you've got questions, please, as always, ask. Have a great day.